Hi, I'm Edith Heiter, a PhD student at Ghent University. Today I'll be presenting our paper titled Evaluating Representation Learning and Graph Layout Methods for Visualization. This was joint work with Kang, Tijl and Jefrey Lijffijt. As we all know, a lot of data comes in the form of graphs, where entities are connected through edges. These can, for instance, be social networks where users are connected if they follow each other, or train networks where edges connect train stations. Prediction tasks on graphs include, for example, labeling new nodes, infer missing attributes, or completing a graph by predicting new connections. Machine learning on graphs is hard because it is unclear how to use the sparse connections effectively. Representation learning has the goal of finding a vector representation for each node such that the structure of interest of the graph is expressed in tabular form. This enables the use of standard machine learning techniques. Interestingly, the designers of some of these representation learning methods also stated that they could be useful for graph visualization, usually by evaluating their suitability to do clustering. A broader comparison with graph layouts has been lacking, despite the fact that graph layout techniques are specifically designed for visualization. In our work, we aim to address this gap by empirically comparing the effectiveness of these two types of approaches. I will now explain our evaluation setup, including the evaluated methods, datasets, and the evaluation measures we used. Then we'll look at the results and discuss the conclusions and limitations of the study. For graph layout methods, we selected Fruchterman-Reingold and dr-graph as representatives. The Fruchterman-Reingold algorithm is a classical force-directed approach, but it is not very scalable. We were intrigued by a new accelerated version that is optimized for GPUs, which is one of the motivations for this study. dr-graph, on the other hand, is based on t-SNE and preserves local neighborhoods by matching node similarities in the high and low dimensional space. For representation learning methods, we chose a diverse set of approaches. AROPE is based on factorizations of powers of the graph adjacency matrix, while conditional network embedding is based on maximum likelihood estimation and can factor out prior knowledge about the graph structure. DeepWalk samples random walks and computes node embeddings based on the skip-gram objective. And finally, graph autoencoders use a convolutional network encoder and an inner product decoder to embed the graph. We used 6 graphs of various sizes and structures to compare the techniques. 3 of them are social networks and 1 is an artificial network shown here on the slide. To evaluate the embeddings, we used measures that are commonly used in the community. Readability of the visualization can be assessed using crosslessness, which is defined as the number of edge crossings divided by an estimate of the possible number of crossings. Another measure is the variation of edge lengths. Here, for example, is one layout where all edges have the same length and one with varying edge lengths. We also used the minimum angle measure, which is the smallest angle between adjacent edges. And finally, the Gabriel shape similarity measure, where we construct a graph from the low-dimensional embedding following the definition of a Gabriel graph, and then compare the sets of direct neighbors for each node. Additionally, we measured the overlap of first and second order neighborhoods in the original graph and the embedding, as well as stress, which is the total mismatch of all pairwise distances, meaning graph-theoretic shortest path distances and Euclidean distances in the embedding. Representation learning methods are often evaluated on link prediction, where some edges are removed from the graph before it is embedded. and the representation is then used to predict the removed edges as well as non-existent edges. In contrast to other measures, this score uses holdout test data that is not seen by the method that computes a layout. It informs about the suitability of the layout to claim that nodes that are close to each other but not linked are likely to be linked to each other. And lastly, we compared the runtime of all methods and we repeated the embedding 4 times and averaged the results for our evaluation. I now give an overview of how we evaluate the methods. We start with an undirected, unweighted graph. We then assess 3 types of embeddings. First, we consider graph layout techniques, which optimize a 2-dimensional placement of nodes. Second, we use representation learning approaches to embed the graph, and we obtain both 2-dimensional node embeddings, but also higher dimensional representations, which we visualize in 2 dimensions using t-SNE. In the following section, I will present our results on the largest graph, the Twitter network. We will begin by comparing the embeddings visually, starting with the graph layouts. We observe that the embeddings generated by Voigteman-Reingold are visually quite distinct. They appear crowded in the center, and the shape of these visualizations is called a hairball. The embeddings generated by representation learning methods have a quite different structure. I would like to highlight the embedding generated by the graph autoencoder. In this embedding, high-degree nodes, meaning nodes with many connections, are positioned on the outside, while nodes with only one connection are located at the center of the embedding, the inner circle. This is due to the dot product decoder used to optimize the embeddings. Finally, we computed high-dimensional vector representations for each node and further reduced them to 2 dimensions using t-SNE. At first glance, the visualizations appear similar, but the local structure differs. If we focus on the embedding generated by the autoencoder, we can observe clusters of nodes having the same degree. In this case, nodes are not positioned close to their connections, but instead they are closer to other nodes with the same connections and the same degree. When we look at the quantitative evaluation measures, for example the crosslessness, we see that the results depend on the dataset. The combinations of representation learning methods with t-SNE are the plus markers here. We see that the graph layouts result in embeddings with fewer edge crossings. For Twitter, the visualizations by conditional network embedding and deep walk in combination with t-SNE also have few edge crossings. For second-order neighborhood preservation, the results are similar, and we observe that almost always the variants involving t-SNE are better than the representation learning in 2 dimensions. For Twitter, the largest graph, the second-order neighborhood preservation for deep walk and CNE in combination with t-SNE outperforms the graph layout methods. The runtime in seconds on all networks shows that drgraph and the accelerated Voigteman-Reingold are very efficient. AROPE is the fastest technique in our evaluation, but its 2-dimensional embeddings are not suitable for visualization. To conclude, our study evaluated the performance of different graph visualization techniques, including graph layout methods and representation learning methods. Our results show that there are trade-offs in terms of their scalability, accuracy, and visual quality, but that no algorithm consistently outperformed the others across quality measures. We found that combining representation learning with dimensionality reduction, such as t-SNE, leads to better visualizations. But in general, we advise using fast graph layout methods and only consider using representation learning when neighborhood preservation is essential or to gain more insights into the method itself. However, we would like to acknowledge some limitations of our evaluation. First, the requirements of a visualization will depend on the analysis task that a user wants to perform on the embedding. For instance, in the two visualizations of a Facebook graph here on this slide, the top one has more varied edge lengths, but better separates strongly connected components, and that makes it easier to identify different clusters. Second, some representation learning methods optimize dot product similarity, which is a different proximity measure than the Euclidean distance used in t-SNE and some of the evaluation measures. So one could adapt the distance-based evaluation measures, for instance, or use a different proximity measure when applying t-SNE. Lastly, using t-SNE after computing a higher dimensional representation of the graph is time-consuming and might not scale as well as faster graph layout methods. We provide our evaluation pipeline on GitHub and Docker such that you can easily evaluate your own graph layout or representation learning approach. Please reach out to us if you have any questions. Thank you for watching.